everyone. Joining us today is Dr. Kris Dorsey, professor at Northeastern University's College of Engineering. Dr. Dorsey, would you like to tell us a bit more about your background in research?
Yes, hi. So thank you so much for the invitation to talk with you. I am a professor of electrical and computer engineering, and I will talk a little bit about what that means in my work and sort of what engineering professors do in general, at least engineering professors at research-focused universities. So to tell you a little bit about my path into engineering and how I got to being an engineering professor, I went to college at a college called Olin College just outside of Boston. And majored in electrical and computer engineering. After that, I went to grad school for my master's and PhD work, again in electrical and computer engineering. And then my postdoc research, which is kind of like you're in a very research-focused position and sort of learning how to ask research questions and carry out your own research. That was at UC Berkeley and UC San Diego, in the Department of Mechanical and Aerospace Engineering. So I would like to tell you a little bit about what I do as an engineer. So when I first started to do engineering research, I was asking a lot of questions related to how we design and build really, really small sensors called micro electromechanical sensors. You might know them as MEMS. And I was working in the applications of navigation and timing. So I was really interested in asking and answering questions related to things like how you design the accelerometer and other systems in your phone, for example, that help you know where you are, to use something like Google Maps, where it gives you the little blue dot to say you're here on this street in front of this building. That's a combination of GPS data as well as things like accelerometers that can tell how fast you're going if you're turning, things like that. So I found that work really interesting. I was really delighted to work on these sensors that were the size of a human hair. But I got really interested after a couple of years in this emerging area of research in using stretchy materials like silicone rubber in order to make sensors and actuators that people could wear on their body, that they could make into soft, squishy robots. So if any of you have seen the movie Big Hero 6 and know about Baymax, so how we might actually make Baymax in the real world and have give Baymax the ability to give someone a hug or to sense that Baymax is picking something up. So those are the sorts of questions that I work on in my research right now, along with my PhD students and the postdocs in my lab. And so I'll tell you three things that I do as an engineer that sort of a lot of different engineers think about as they work and that I think about in my lab. So one thing that engineering researchers do is use mathematics and science principles to predict how something is going to behave. So for example, in my PhD work when I was in grad school, we were trying to figure out how these accelerometers, these things that we're using for navigation and figuring out where we are in the world, we were trying to figure out how they would react if we changed the acceleration that we were applying to it. So let's say someone was standing still and then they started jogging. What would the sensor's response to that be? So we used physics and math models to predict how the accelerometer would react to that. That's this kind of cool equation on the left. I don't want to go into what the equation is telling us, but I do want to share that's one thing that a lot of engineering researchers do, is use these principles to understand how the things we're building are going to behave in the real world. A second thing that a lot of engineering researchers do is make experiments to understand why things don't work the way we think they should, based on our initial models, those things that I described on the last slide. And so the video that I'm about to show you is a material that we use in my lab called liquid metal. So it's a material that behaves like a metal, it's electrically conductive, but it's actually liquid at room temperature. It's not mercury, so it's safe for people to use and be around. And what this video is showing you is I'm injecting this liquid metal into one of our sensors. There's a little channel that it's really hard to see because the whole thing is see-through, but a channel in this sensor that the liquid metal can flow into. And so you see it actually is behaving like a liquid. So when I was working with this material, I was applying a current to it to heat it up, kind of like you apply a current in a space heater if you use a space heater radiator at home. And something I noticed was that I could apply this current and these liquid metal devices would last for a couple of hours and then they would break. They just wouldn't work anymore. I couldn't apply a current anymore. And I was really frustrated because I needed that to be able to do the rest of this project. And I talked to a colleague, I talked to a friend at another lab in another part of the US, and I said, I know you work on similar things. Have you seen this behavior? And he said, yeah, I've noticed a similar thing. I apply this current, it works for a couple of hours and then it breaks. And so we said, okay, we're gonna make some experiments to understand why these liquid metal wires are breaking. Why aren't they working the way that we think they are? And so we got to do a lot of really fun stuff here. We built a lot of devices. So these are the liquid metal wires in this photo kind of right in the middle. And then we saw for different currents that we were applying, how long the wires would survive. And we saw that if we applied a really low current, the wires would last for, this is almost a week. But if we applied a lot more current, the wires would last for just under 2 minutes. And then we also got to use an infrared camera to see where the wires were heating up. So that's this photo in the bottom right. And it's showing that there's a hot spot, that there is one little part of the wire that was heating up really, really fast, and then kind of breaking itself because it got so hot. It almost burned out. And so we got to do all these experiments and then write up our findings to not only understand ourselves why these liquid metal wires weren't working the way we thought they should, but to explain to other scientists and engineers and other people that might use liquid metal why this liquid metal wasn't working the way that we thought it would. The last thing that I want to tell you about from my work that a lot of engineering researchers do is make new things and test to see how they work. So something I'm really interested in my work is origami materials and how we can use origami principles and origami-like materials to make robots that are made out of paper, that are made out of rubber, they're made out of plastic. And so I'm showing you a couple of examples. Most of these are not my work. These are other researchers, other engineers and scientists that are building these systems. And some of the things that people have thought of are using these little origami modules that go from a flat state to an expanded state as sort of an additional arm that might sit on your wrist. So you could use it as another arm. Some other ones, someone made a really cool robot juggler that can juggle balls based on if the origami is expanding or contracting. And then my work was in making different origami shapes and understanding how that changed some sensor performance that we were really excited about studying. So with these projects, I wanted to show you kind of both what I work on and sort of how engineers and engineering researchers think about questions and sort of different things that they do day to day. Sometimes I might be designing an experiment, sometimes I might be carrying it out, sometimes I might be looking at the data that we collected and going, we thought that we were going to see this happen, but we actually saw this other thing happen. That's really interesting. Why did that happen? Sometimes we'll be writing up our results into a paper that will allow us to share and communicate with other engineers or scientists or policymakers, healthcare providers, the wider world. Sometimes you'll see in the news things about scientific studies, and a lot of the times you'll hear about papers that those results are based on. And so that's a lot of the time how engineering researchers communicate what we've learned in the lab. So with that, I hear there's a little bit of question and answer, and I would welcome some questions about what I just talked about.
Thanks so much for presenting, Dr. Dorsey, and now we'll move on to the Q&A segment.
Yes, the first question we had for you was how accurate are your micro electromechanical sensors compared to the regular sensors?
So this is one of the really interesting things that we talk about in engineering, this concept of trade-offs. So you might have a trade-off between cost and how the performance of the sensor, how good it is. And so you can design sensors that may be low cost, but may have a lower performance, or sensors that have a really, really good performance that can sense how, for example, how fast the Earth is rotating, which is 15 degrees an hour. But those sensors are more expensive because they're made out of more expensive materials. They require a tighter, a more specific fabrication process. So it really depends on what the application is and what the trade-offs are that you have to think about.
Got it. Yeah. We're also wondering, what is the real-world applications of origami-like mechanisms?
Good question. So I will show my slides for just one more second so I can talk about one of the applications. Are they showing up again?
Yeah.
Okay, great. So in this bottom right figure, this is an origami gripper that is based on a well-known pattern in origami. And they're using it they've got this gripper on a robot arm. And what the gripper does is it's normally kind of expanded. And when they apply a vacuum to the gripper, it contracts. And if it contracts around something, it'll pick it up. Kind of like if you've seen some of those cranes in like an arcade or something where they can go and grab a stuffed toy. It's a little bit like that, only the gripper is known as what it conforms around something. So it follows the same shape, so it can pick that thing up really well. So instead of designing different claws or different hands that can pick up a can of soup or a glass or a water bottle, this origami shape can pick up all of those different things because it conforms to the shape. So gripping is one area where roboticists and soft roboticists talk a lot about the applications of origami. Another is robot arms. So instead of having a big metal arm like this, we could have an arm that can fold or expand like these arms in the bottom left. And the advantages for that then, if they're made out of paper or plastic or rubber or something like that, they're much softer. They're gonna be able to work with people because there's not as much of a danger about someone running into an arm or an arm running into a person. And they also may end up being less expensive than this metal arm, which is really, really high performance, but also really expensive.
Yeah, that sounds really interesting. Maybe just another question we had was, what inspired you personally to pursue a career in electrical and computer engineering?
I think I have always been really interested in how things work. I am one of those people that likes to take things apart and likes puzzles. And so the different aspects of engineering where you're trying to solve this mystery, why does this work? Or why doesn't this work? Or how do we make it work better? Or how do we design something new? I really liked those questions. And specifically with electrical engineering, I always found it kind of really cool and mysterious how we do things like apply a voltage or apply a current, and can use those ideas to do everything from making your computer work to sending radio signals through the air so that we can talk to each other. All of those are sort of electrical and computer engineering based questions. And I just really found that fascinating when I was learning about different types of engineering.
Got it. Yeah, I just I guess one more sort of technical question here. Like, what challenges do you face when building the soft sensors for soft robots and the wearable medical devices?
That's a really good question. So I think one of the challenges that I didn't realize when I first started this work is that everyone is sort of using their own process. So the way that we make the sensors is because people are still doing research in what's the best way to make the sensors and how do we make sensors that give us this particular output or give us this particular performance, is that I may learn about a process that a friend of mine is doing in another lab. I may learn about it from a paper and try to do it in my lab, but the temperature is slightly different, or the humidity is higher or lower in my lab. And because these materials are really sensitive to those changes, my sensors may behave differently than theirs do. So environmental conditions is a big one that if we're not tightly controlling those conditions can really change how our sensors behave.
Okay. Yeah, and just our final question was, how can high schoolers dive deeper into robotics?
I think there are a lot of really great ways that high schoolers can get involved in robotics. So if you have a high school robotics team, that's a great way to get involved. But there are also lots of robot kits and YouTube videos and other things where you can get a robot platform like Lego Mindstorms or a Vex kit or something like that, and just try to start playing around. One of the things I think is really, really cool about robotics is it combines so many different skill sets. There's the actual putting the robot together, the mechanical engineering part. There's the coding. There's the sensor integration, so figuring out how our robot understands and perceives our world. That there's always something different and new to work on, and a lot of variety in the challenges in robotics.
All right, well, that's all the questions we have. So, once again, thanks for coming, and thanks so much for watching our interview with Dr. Kris Dorsey. Take care, and we'll see you all next time. Bye.
Bye.